So first of all, I need to finish up something from the last lecture that I didn't get around to. But it's a good place to start the current lecture because it will remind us of some concepts. So I want to show you how to prove very briefly the following important fact, that whenever I have a category of diagrams like this, or also called presheaves on some small category, that this is an example of a Cartesian closed category. And these are, in some sense, certain very simple and useful Cartesian closed categories because you have a kind of intuitive idea of what they are. They're some kind of variable sets. Right? They're sets that vary in a parameter coming from the index category. So it was a homework problem to show that these things have products. So if I take two such variable sets or diagrams, that I can make the product, and I think I told you how to do it. I said for every object X in the category C, let the product simply be the product of the values of these two functors. So we're going to make the products pointwise. This is pointwise. And then whenever X goes to Y, well, this is contravariant, so whenever X comes from Y, like that, we need to find a way for this thing to go to this one. And how should we do it? Well, the value over here we've already decided is going to be this. But now we have to get from here to here. Well, that's not hard because associated to A itself, we're already assuming is an action on this arrow, right? So there's some thing right here, right? Let's call this map here H. Well, then A acts on H here, and A also acts on, or B also acts on H, and now we know that the product is a functor, so producting up those two maps gives us the map that we're looking for here from AY to BY. Yes? So that was the homework problem. I don't know if anybody did it, but it's very straightforward to show that you can make products like this pointwise. And in fact, you can also make coproducts pointwise too. So I don't have a thing here. So here, same for A plus B. You can make those things pointwise too. But what about the exponentials? That's the interesting thing. So exponentials. What are we going to do about B to the A at X? Well, the first thing you might think of trying is just to make that pointwise too. That certainly is the first thing to at least try and see if it works, right? So let's take that set where the values here are in sets. So for two sets, you can always make the function set, the set of all functions from one to another, right? And now here's again Y coming to X. Well, let's see here. We have B, we have A. Where's the? So we need to get to B to the A at Y, which we're wondering maybe could be defined like this. So we need to get a map. Sorry. We need to get a map like this, right? That's what we need. So we've got B X to BY by assumption. We've got AX to AY by assumption. But of course, there's a problem here because this is in a covariant position and this is in a contravariant position, right? So from these two maps, what can we put together? Well, we get BX AX, and then here's B, let's say X AY, BY, AX, BY, Y. So from this map here, we can just compose with this map we get a covariant action like this, right? This is a to the x is fixed up in the exponent there. And similarly here, a to the y is fixed up in the exponent, so we've certainly got a map like that. But from this map going from ax to ay, all we can do is precompose, and we get a map going this way with the by x fixed, and with the by same thing. But remember, we're trying to get this, so we're stuck. Yeah? There's no obvious way of using the action on b and the action on a and putting them together to get an action on this exponent. So the result of this is that this does not work. Does not work. So the exponent, if it exists for two functors, is not going to be given pointwise. So now what do we do? Well, what to do? Well, you could guess, try to do some stuff, right? You could say, oh, well, if they're isomorphisms, then I could turn this one around somehow, and then they would be composable. Or you could take embedding retraction pairs, and then you could take on the one hand the embedding and the other hand the retraction, and so on. So there are lots of different techniques you could use. However, it's better to approach it in a principled way and try to see what it has to be, right? And then see if that works. That's kind of the machine of category theory gives you a way of testing what things ought to be and then deducing what they are going to be if they exist. So again, as in many cases, it's Yoneda to the rescue. Yoneda to the rescue. So let's do it like this. We want to have, we're looking for a functor b to the a, and we're trying to say, what the heck is it? Well, Yoneda tells us what it ought to be. If it exists, we know that it's got to be this. Right? Everybody remember the Yoneda lemma? Yoneda said that for any presheaf f, f of x is hom of the representable into f. That was the Yoneda lemma. Put it on a t-shirt. So let's use it. If this is going to be an exponential, then that's going to be isomorphic to hom yx cross a b. Right? If it exists, it's going to be that. So let's see if that works. Does this give us a contravariant functor of x? Contravariant variant in. So the proposal is we're going to take this as the definition right there. I mean, that's a set, right? This is a set of all natural transformations theta from yx cross a into b. That's our proposal for the value of this exponential functor at x. Yeah. Is it a contravariant functor of x? Well, let's see. We have, let's suppose that y goes to x. Well, we know the Yoneda embedding then is a functor, so that gives us this. Now we can cross that thing with a, because that's a functor, so that gives us this, yx cross a. And now we're homming out of this thing in this expression, right? So that gives us hom yx cross ab. This is a contravariant functor in the left-hand argument, so that gives us this, hom y cross a. So yes, good. It's a contravariant functor of x. If y goes to x, this thing goes to that thing. So we're done. And now you check, and now defining this to be the exponential, you go back through and check that this holds. I mean, this is the calculation which tells you that it's an exponential. So now what if you look at this thing and you say, oh, that's nasty, I don't like that. Tough luck. I mean, that's what it is. We just computed what it's got to be, and that's it. So the thing to do is just to get used to it, right? Start working with it, get a feeling for it, see what it means in some special cases and so on. But we know that if there is an exponential, this has got to be it.
Does it mean there is another way to express it
Absolutely, sure. I mean, this is an expression and it works. And now you can start calculating with that expression and find other ways to describe it that you like better and so on. But any other way that you come up with will be isomorphic to this one. So this at least proves that there is one, and this is a particular expression of it.
Is there another one you like better?
Depends on the special case. For the case where C is a poset, there's a very simple description of what this thing means, and it was one of your exercises. It was the last exercise. It's a kind of restriction operation. And yeah, I like that one a lot better. It's easier to work with. Okay, so that's our proof that variable sets is a Cartesian closed category. And in fact, there's a corollary now, because we know that, oh wait, there's one thing I didn't do. Oh, let's, first of all, we'll say the Awodey embedding itself from C into sets to the C up. Now that we know that this thing is Cartesian closed, let's suppose that this one is also Cartesian closed. We can show now that that preserves Cartesian closed structure. In fact, any Cartesian closed structure that this thing has, even if it only has partial exponentials or only products for some objects, they get preserved going up to here. So let's check that. So products, if we want to make Awodey of A cross B, what is that? That's Hom blank A cross B. Well, we already checked that you can pull a product out on the right of a Hom set, right? A cross Hom B. So that's Awodey of A cross Awodey of B. Because we know that these are taken pointwise, we just checked that the product of two functors is just the pointwise product of the values. So that's what we've got here. So that's good. And now what about exponentials? What is Awodey of B to the A? Well, it's Hom B to the A. Let's give it an argument. So x. So we'll put the x in here. Right. I'll do it down here. X cross A, assuming that this really is an exponential in C. And now we use the Awodey lemma again. The Awodey lemma tells us that we can apply y right inside here and still get an isomorphism. YB. Because remember, this embedding establishes an isomorphism between these two Hom sets. So that's iso. And now by the first part that we just checked, this y distributes over x cross A. So that gives us Hom yx cross ya yb. But hey, look at that formula. That's this. That's this formula for the case that this thing is ya and this is yb. So that is exactly y to the b, y to the a applied to x. So there we go. Okay, so now the Awodey embedding preserves Cartesian closed structure. It also gives us an isomorphism here between the Hom sets in here and the Hom sets in here. And now a consequence of that, remember we had our theorem on the completeness of the lambda calculus with respect to Cartesian closed categories, with respect to abstract models in Cartesian closed categories. Well, now we know that every Cartesian closed category embeds into one of this very special form, a Cartesian closed category of variable sets. Right? So this corollary says, in particular, given any Cartesian closed category, we can embed it as a Cartesian closed category into one of these special ones consisting just of variable sets. So in particular, if we're interested in completeness of the lambda calculus with respect to some particular class of models, we already proved it with respect to the very general class of all Cartesian closed categories. But each of those embeds into one of these very special ones of variable sets, and so we get a completeness theorem with respect to variable sets. So this completeness of the lambda calculus or simple type theory with respect to, well, variable sets. Variable sets. And the statement of the theorem is basically the one that I wrote down before, right? It says, given any, I'll just do it briefly here, given any terms in the lambda calculus, any lambda theory with basic types, basic terms, and equations, basic equations, any lambda theory, and any terms, let's say S and T, of any type X in that theory, if the theory proves S equals T modulo the basic equations of the theory, then for any interpretation of the lambda calculus into a Cartesian closed category of this special form, interpretation into any Cartesian closed category of variable sets, the interpretations of those two things will be the same. So this direction is, of course, soundness of the lambda calculus with respect to the semantics, and this direction is the completeness. If the terms come out to be the same under all interpretations in variable sets, then they must be provably equal via beta-eta conversion. Okay? And then there's a similar statement about inhabitation of types. So there's a term T of some type X if and only if in every model there's a term, there's a closed term T of type X, there's an arrow from the terminal object into the interpretation of X. So that's provability in terms of, so it's provability in terms of inhabitation, and it's provability in terms of the convertibility of the terms. It's completeness in terms of convertibility of the terms. And this follows now, so by variable sets I of course mean things of this special form. And that follows from this embedding theorem that we just proved. And in fact, there's an even stronger version. Here. I'll write it with capital letters. And the stronger version was actually proved only recently by me. And there's a paper by me and a student named Florian Rabe, which was in the recent, I think it's, I don't remember you'll see the reference if you just Google it. And this is a Kripke completeness. And this says same thing with respect to categories of the form sets to the P, where P is a poset. And that's a stronger, even stronger condition, or even smaller class of models, which agrees with conventional Kripke semantics, where you have, think of the poset as the poset of possible worlds in a Kripke frame. The ordering on the worlds is just the accessibility ordering, and then there's a very neat description of what it means to be a model of the lambda calculus in such a setting. That gives you a Kripke model of the lambda calculus. The types are just domains varying over the possible worlds. The products are pointwise. The exponentials are the thing that you asked about that I mentioned before. They're very nice restriction operations. And that's a complete semantics for the lambda calculus. Okay, so that completes the last lecture. Let's go on to the next lecture. Yeah, sure. It's a good time for question. Yeah.
Could you say a little bit more about this variable sets intuition?
Oh, sure. Yeah. Happy to. Let's look at an example that we had before was this sets through time. So there the poset was just omega, it's 0, less than 1, less than 2, and so on, forever and ever, right? And then an object in here, A, is just a set changing through time. So there, right, we have, it's a sequence of sets, and the elements change as you go from one to the next. You think of it as the set is developing through time. Some elements come in, some elements get identified, and so on. And then the arrows we saw were those ladders of functions, yeah? But equally well, you could have a different poset. So let's say we parameterize this where P is something like binary trees, something like that. Or P is a binary tree. So something developing like that. Well, then what is a functor on that going to be? Well, it's going to be a system of sets with some branching like this corresponding to this branching of the trees. So as the thing develops, the sets develop in different ways. It's not just omega sequentially, but whatever the poset gives you for an ordering type or for a branching type, the functors have to respect that branching type. So maybe you have the total binary tree, right? So at every moment there are two possibilities. Or maybe you have a poset. Another possibility is maybe your poset is the real numbers. And then you have continuous time, right? So you don't have this discrete nature, but for every two reals or for every two rationals, say, there's a way of connecting them. So there are lots of different examples like that that you can think of. Maybe the poset is, for example, all the open sets of a topological space. Right? And now you think of the space here, and then you think of the open sets and their inclusion ordering. And then the poset will assign to each open set for each region. Think of the space maybe as physical space, and think of the open sets as regions, right? And for each region of space, the functor will give you a value on that region. Maybe it's all the real valued functions defined on that region of space. And then as you go down, usually these ones are taken to be contravariant. So maybe as you go down from one region to the next, maybe the functor A takes this to all the functions, say, in the reals, and then defined on this region. And then as you go to a smaller region, you just restrict. So F goes to F restricted to the smaller region. That's actually the classical example of a presheaf. That's where the original definition comes from, is that idea of functions defined on regions of a topological space. But the idea is the same in all cases. It's a set which varies in a parameter. Right? In all cases, we have some poset. It has some elements, and they're ordered in some way. And then a functor on the poset is a family of sets, one for each element. And then every time you have an ordering like that, there's some way of changing from one set to the other. So that's the idea of variable sets. That's enough?
Yes, and it raises another question.
Okay.
So in both of the examples that you chose, the natural ordering on the exponent set was one way, and it looks like an op disappeared with respect to the generic discussion.
Yeah. It doesn't matter. I mean, it's perfect. It's purely a convention whether you order things one way or the other. Right? So I could have said order the numbers going the other way and then put op up here, something like that. This one became an op because it's a restriction operation. Right? So that's just conventional. I mean, every category has an op, and the op of a category will be op it to pick the category back out. So, is there another question? Okay, so what I'd like to do now is that's finished. Now I'll go on to another lecture, a whole new lecture. Okay, so now lecture 4, for which I have less time than I'd like, but it's worth at least getting started, is on adjoints, adjoint functors. And really, this is the most important of my 4 lectures, because adjointness if you take away anything from these 4 lectures, I would like you to take away the idea that adjointness is a fundamental, foundational concept of the greatest importance, which has been completely invisible and unrecognized until the advent of category theory. You need to have category theory in order to recognize the concept of adjointness and then develop its basic properties. So that's admittedly somewhat provocative. I mean, most people involved in foundations or logic would say something like, oh, maybe the notion of a type, or if you're a set theorist, the notion of element, or I don't know what, the notion of a function or something. But I'm going to say no, adjointness is maybe the unifying, I could be even more provocative, I could say it's the most important unifying concept in foundations of mathematics. Okay, so that's a big claim, so let's see how far we get with that. Let me just give you a couple of logical examples, which I hope to be able in the next few minutes to at least sketch. So one example of an adjunction is the adjunction between taking the product with something versus, this is how it's written, I'll explain it in a minute, versus taking the exponent by something. So this captures the basic operations of the lambda calculus. Another example of adjointness is the product operation itself. We'll see in a minute that that's adjoint to a certain trivial operation that you may not have even recognized, but it's there. And moreover, that's adjoint on the other side to the coproduct operation. So these things are related to each other in that way. Also, the notions of induction, recursion, and then things defined in terms of them, like the natural numbers and types of lists, all kinds of inductively defined types. These are all examples of adjoints. And similarly in logic, of course, things related to this, like conjunction, disjunction, true and false, exponentiation. These are adjoints. Also, the quantifiers. I think it's quite remarkable and beautiful that the quantifiers are examples of adjoints. And even in dependent type theory, the type theoretic operations on dependent types, sigma and pi, are also examples of adjoint functors. So if I can show you that all those things are adjoints, then maybe you'll believe me, or at least you'll understand my rhetorical flourish of claiming that adjoints are a concept of fundamental logical and mathematical importance. Actually, these are just a few examples that occur in logic. But actually, adjointness occurs all over mathematics, from the highest level, from the lowest foundations to the highest abstract constructions in mathematics. There are examples of adjoint functors. So let's start with that first example of product and exponential in order to get the general notion of an adjunction. So here's our example. So we saw that when we have products and exponentials in a Cartesian closed category, there's a bijection between things of this kind, that is, arrows out of a product, and things of this kind, So here, fix A in some Cartesian closed category C. There's a bijection between things of that kind and things of this kind. Right? And that's the fundamental operation of currying or evaluation, which mediates that bijection. Given something like this, you get one like this. Given something like this, you get one like that. And moreover, if you compose those operations, you get the identity back out. Okay, so what we have here is, on the left, we have a functor, And we've checked that that's a functor, right? F of x, namely it's x crossed with a. We know that that's a functor. On the right, we also know that this is a functor. Call it g of y, and it's y to the power of a. And we have an isomorphism between maps out of F and maps into G. And moreover, we know that this isomorphism, so we have an isomorphism between, but moreover, the isomorphism, as we said before, doesn't really depend on x and y specifically, right? It's parametric in x and y, or it's polymorphic in x and y. It's an isomorphism between these two structures of product with A and exponent by A. And we learned last time how to say that. It's natural in x and y. It's an isomorphism, and it's natural in both arguments, x and y. Well, that's the definition of an adjunction, exactly there. So the definition is this. An adjunction between two categories, say, between categories C and D, consists of, so here's C, here's D, a pair of functors, F and G, going back and forth. In this case, the functors were on the same category C, but that's not essential. We can have an adjunction between two different categories, such that there's a, well, such that, wait a sec, don't write things down until I've finished because I might change it. I'm making this up as I go along, you know. Such that for all x in C, y in D, there's a bijection, well, of exactly this form. F of x into y corresponds bijectively to x into g of y. And moreover, it's a bijection, it's natural in x and y. Good. So that's the definition of an adjunction. Just by way of terminology, is this pen running out now? Or terminology. So in this case, I'm going to say F, and I'm going to write a backwards turnstile G, just because that's the convention. And we call this one the left adjoint for obvious reasons, left adjoint. And this one is called the right adjoint. And so we already had one example. That is, we showed, well, number one over there, right? We showed that the operation, the functor cross with A, is left adjoint to the functor taken exponent by A. So that's our first example. Right? Everybody good? That's exactly this example. Let's do another one. Remember, in the case of products, we said x into A and x into B gives us a map x into A cross B. Going back and forth, right? We said that's the universal mapping property that characterizes products, that defines products. But let's look at what's going on up here. What is that? X into A together with X into B. Really, we can put that together as a single map of the form X, comma, X goes into A, comma, B. That's a map in the category C cross C. So what's above the line here is exactly a map in C cross C, whatever our category C is, right? And this is an object of a special kind. Let me call it delta of X. So down below here is C. So what is delta of x? What do I mean by that? Well, let's do it this way. I have a functor. Here, I'll just write it right here. C cross C. I have a functor delta going up into C cross C. It takes an object x and it just pairs it with itself. It's a very trivial kind of operation there, right? Remember, the objects in here are pairs of objects. Right? Here I take a single object, I bring it up here, and I take just the object paired with itself. And that's exactly what's going on here on the left, is such a delta. And now I'm saying, map that into anything. That's what's happening on the top of the line. That will correspond exactly here to the product of A and B. So on the top of the line, I have something like this. And on the bottom of the line, I have X mapping into A cross B. So that's exactly saying that this operation delta is left adjoint to the product operation. Good? Everybody see it? Yep.
Could you unpack what it means that bijectioning in the definition of adjunction to be dashboard X and Y?
Let's do it later together, okay? If you work it out, you'll get it. It's just time consuming, and I don't have the time to do it, okay?
What is the functor G
Here,
here? Yeah.
the product functor. It takes two objects, A and B, and it takes them to their product. Is it good? The left adjoint is delta. The right adjoint is the product. You know what? There's another adjoint over here, a left adjoint to delta. Should we see what it is? How would it look? It would go like this. Anybody guess? Oh, I'm sorry, I already gave it away, didn't I? Okay. So it goes like this. Over on the right, I put delta x, x. So what's that? That's x, delta x. So what's that? That's x comma x. And now I map into it by A comma B. So what's that? That's a map from A into x and a map from B into x. Well, so now I'm asking for a left adjoint to delta, so that would have to be something here and a map into x. Well, we know what corresponds to pairs of maps like that out of A and out of B. It's exactly, it's exactly A plus B. That's the universal mapping property of A plus B, isn't it? That a map out of A plus B is a pair of maps, one from A, one from B. So the coproduct here lives on the left. And now it's time to, maybe I shouldn't erase that. And now it's time to, there's that, A plus B. And now it's time to say something here about the uniqueness of adjoints, because it's quite important. These things that I'm producing here are things that before I characterized in terms of universal mapping properties. And I emphasized that every universal mapping property determines its object uniquely up to isomorphism. Well, it's no coincidence that these things are all adjoints, because adjoints are unique up to isomorphism. So that's the important fact that we need to know, and that's what underlies the idea of adjointness as a construction principle or generating principle for new mathematical constructions. Is whenever you have a given operation or functor, and then you ask for an adjoint to it, that's a condition on a construction, namely being adjoint to an existing thing, which will determine that thing uniquely up to isomorphism. That is to say, to put it differently, often you have a very trivial or maybe even unnoticed operation like this one of doubling something. And then the condition of being adjoint to it will be an interesting and important construction, and that construction is uniquely determined up to isomorphism by that condition that it's adjoint to this other given thing that you haven't even been paying attention to maybe. So the fact is, adjoints are unique up to isomorphism. So you can define something by saying it's adjoint to this other given thing. Yeah?
We define view of the product, and
Yeah.
it looks like it's used in this, or it relates to the one that we have.
Yeah, that's good. So take C and now take the up everywhere, and this product will go to the other side, and this one will come to this side, and this will become a right adjoint.
Does this work for other adjacent pairs?
It works for some, not all. I mean, you can always take a junction and dualize it and get an adjunction. But you can't always get some new further thing over on the other side. That's special condition. So what does it mean, unique up to isomorphism? Let's do it like D and F and D and G and say G1 and G2. And I want to show, and both of these guys are left adjoint to F. Then I want to show that G1 and G2 are isomorphic. That's what it means to be that adjoints are unique up to isomorphism. Well, again, how am I going to show it? Let's try the Onedo lemma. If you don't know what to do, that's always a good thing to try. So let's try, I want to show that G1 of, say, Y is isomorphic to G2 of Y. So let's try HOM X G1 of Y. Oh, but that's a right adjoint. So let's get it out of the way. Fx of Y. But there's some other right adjoint of F, namely G2 of Y, by the assumption that those things are both right adjoint. And so we've shown that HOM G1, of course we have to show that this is natural, but we're assuming that the adjunction is natural. That's part of the definition. So there we go. And now Yoneda gives us what we want, right? By Yoneda, G1 is G2. Mm-hmm.
In the diagram.
Okay, so we can use the adjunctions to describe or axiomatize, define constructions in terms of other ones. Let me see, what did I want to do next? Yeah. Before doing some more examples, let me observe that there is an interesting consequence here of this characterization. Accompanying any adjunction are some distinguished maps that are, of course, important. So given an adjunction, say F left adjoint to G, let's look at the following. Suppose I take F of X above the line here. So, of course, F of X into Y corresponds to X into G of Y, right? But let's put in, as our Y, let's put in F of X itself. And we'll put in here the identity map. Yeah, that's a valid entry for here. And now down here, I get a map from X into G of F of X. So whenever I have an adjunction, for any object X, there must be a special map like this. And this map, which is conventionally called eta, is called the unit of the adjunction. Unit of the adjunction. And of course, there's a similar thing I can do. I can say, let's put in G of Y here. G of Y. And then up at the top here, I get F of G of Y going to Y. So for every object Y, there's a special map like this. That one's called epsilon, and that's, of course, the co-unit of the adjunction. So let's see some examples of these units and co-units, because these are going to be, obviously, maps that are somehow interesting. So, for example, in our case of product with A being left adjoint to exponent by A, if we compute the co-unit, what we get is the following. This is our F. This is our G. So we get, for any y, a special map y to the A cross A, right? Because that's F of G mapping down to y. Hey, look at that. That looks familiar. That co-unit of the product exponential adjunction is evaluation. The evaluation map that we all know and love is distinguished as the co-unit of the product exponential adjunction. I have to leave some homework exercises for you, so you'll do the unit. Okay? How about the delta is left adjoint to the product? Let's do the unit. So that's our F, that's our G. Let's calculate the unit of that. So for any x, we have to have a map into the pair x comma x, and then we apply the product. We get x comma x. What could that be? The unit of the product adjunction is, of course, sometimes called the diagonal map, the map which takes every element in x to its pair x comma x. Diagonal. What's the co-unit? Well, I'll let you work some of these out. The co-unit is going to be a pair of maps because it lives in the category C cross C, and though it's of course going to be the two projections from the product. That'll be the co-unit. And then, of course, there are the units and co-units for the sum as well. So anytime you have an adjunction, you're going to want to ask yourself, what's the unit? What's the co-unit? Because these are going to be important maps. All right, let's go on now to some more examples. Good. So what I want to do now is some adjoints in logic. Well, we already saw before that, for example, if we look at the propositional calculus, we can characterize conjunction as a product in the category of proofs or the category of provability, right? But now we know that products are adjoints. So of course we have the product, right, with its usual rule, say that the usual rule for products we could express, for example, like this. We could say, let me do it like this. Let me start over a little bit. Let's set up a propositional calculus like this. We'll have expressions of the form P entails Q, and we'll have a calculus of such expressions, binary sequence. Yeah? And our axioms will be the following. We'll say it's reflexive, it's transitive, and then so the propositions form a category, and now we'll start stating our rules of inference motivated by or led by the idea that the logical operations are all examples of adjoint functors inside this category. So for example, for conjunction, we'll use the usual product rule. We'll use the usual adjunction characterizing product to give us the rules for conjunction. So we'll say, for example, phi theta. How do I want to do this? No, I want to do it the other way. I want to do a two-way rule of inference that says if theta proves phi and theta proves psi, then theta proves phi and psi. There we go. So that's the rule for conjunction. For disjunct, so this is just saying that we have the usual product adjunction now, right, with the product on the right and the delta operation on the left. And similarly for the coproduct, we'll go the other way. as a two-way rule of inference again. So there's a calculus for product disjunction. Of course, we can put in the, I haven't talked much about the terminal object, have I, or the initial object, but these are examples of, I can put in anything here really. These are examples of simple adjunctions. I'll let you work them out yourself. The adjunction that characterizes a terminal object or an initial object looks like this. Terminal object. I defined this before, didn't I? Terminal object. One in a category. Did I say that? Okay. How do I define a terminal object as an adjoint functor? Look at the functor, which for every category takes the category down to the one object category. It takes all the objects in here to the one object in there, and it takes all the arrows in here to the identity arrow on that one object, right? So that functor, I claim, has a right adjoint, and that right adjoint picks out a terminal object in C. So that is to say, for anything in C, there's an arrow to 1 just in case this of C maps to the unique object in this terminal object category. So there's that, and there's that. So C has a terminal object if and only if this unique functor, which exists for every category, has a right adjoint. And similarly, it has an initial object if this thing has a left adjoint. So there's the description of these things as terminal and initial object as adjoints. And then the only thing left is the implication, and we know how to do that. That's phi psi proves theta, if and only if phi proves psi arrows theta. So that's the whole propositional calculus in terms of 1, 2, 3, 4, 5 adjunctions. Let's continue now and look at the quantifiers, because that's, I think, a really beautiful insight due to Levier. Actually, this analysis of adjoints in logic is due to Levier, I should say. F W Levier. And the emphasis on adjunction as a foundational notion is also due to Levier. Although he didn't discover adjoints, adjoints were discovered by Daniel Kahn in the context of algebraic topology. There's a beautiful paper by Levier called Adjointness in Foundations, where he lays out all of the basic foundational operations as adjoint functors. I definitely recommend it. (1964), something like that. So let's do quantifiers as adjoints. So let's extend our calculus now to include formulas with variables, like predicates with individual variables. So we have some domains of individuals, and then we have some primitive predicates or relations over those individuals, maybe including the identity relation. And then we build up formulas involving some variables, right? C, x, y, etc. In the usual way, right? Maybe we say for all x, there exists a y such that r have some primitive relation here, implies there exists a z such that p of z, something like that, right? So we make some first-order logical formulas like that involving variables and quantification and the other propositional operations. And now let's look, and then we're going to have a calculus or a deductive system as before. Of entailments phi x psi right, with possibly several variables here. That I don't mean to suggest some restrictions here. C, Y, Y. We'll keep things binary just to keep it simple here. So we have a deductive system of such entailments and then some rules of inference that we use to manipulate those. And now let's consider the following. There's an operation a very trivial operation of adding a new variable to a context. What do I mean by that? Well, if I have phi and I think of this as a formula in these variables, then I have, so this is a formula, say, in variables x1 through xn. Well, then I can think of this also as a formula in variables x1 through xn, and a new variable y, which doesn't happen to occur in phi, but I can regard phi as a formula in more variables, x1 through xn. And what do I mean by regard it as a formula in more variables? Well, what I mean by that is I can compare it to other formulas that might have that additional variable in it. Like I can consider implication x1, xn, y, a relation of implication to a formula that does have a y in it. So it may be that although phi doesn't have a y in it, so it lives in this set of formulas with variables at most in here, it also lives in this set of formulas with variables at most these. Good? And now the operation of regarding a formula as having more variables than might occur in it is the fundamental, trivial operation that we're interested in, because this operation has adjoints. So for example, the right adjoint here of that trivial operation is the universal quantifier over y. Let's see that that's true. Let's suppose that phi of x1 through xn does entail psi of x1 through xn with a y in it. Well then, the rule of inference for introduction of the universal quantifier says that this holds for all x, 1 through xn, y. Everybody recognize that rule of universal introduction? The rule of universal introduction, the way it's usually stated, says if you can prove this thing from assumptions that don't involve y, then you can prove it for any y. And moreover, you can go back. Because if you can prove this for all y, well then from this you can prove this by a universal elimination, and so you can prove this. And so we've just shown that this trivial operation here, which I'll call star, is left adjoint to the universal quantifier. Now, of course, the next thing we're going to look for is maybe there's another adjoint here. What could it be? Let's set it up here. So it says if we can prove from phi x1 through xn. And now we've got some psi over here, x1 through xn, with a y in it. If we can prove from an assumption involving a y something that doesn't depend on the y, right? Isn't that exactly the existential introduction setup? E, y, psi, x1, xn, y proves phi x1 through xn. And again, if we can do this, then we can do that by a universal introduction. So of course, this is the existential quantifier. So the quantifiers in first order logic are left and right adjoint to this trivial operation of regarding a formula as having another variable in it. And moreover, because of what I said before about the uniqueness of adjoints, all of the fundamental properties of quantification are determined by this fact. This uniquely characterizes the quantifiers. And the quantifier rules of inference, including the tiresome bookkeeping side conditions on variables, right? When you learn the deductive calculus for first order logic, you have to remember now, no y in C, or what is that bookkeeping side condition? Those things are not a nuisance. Well, they are a nuisance, but they're an essential nuisance, right? You need to have those rules in order, those bookkeeping conditions, because that's what the quantifiers are adjoint to, the presence or absence of variables in the given context. So that's the specification of the quantifiers. And of course, the things I mentioned before are things like this: for all y, c of x, y proves c of x, y. This is, of course, the co-unit of that adjunction, right? If you ask yourselves, what are the units and co-units? They're going to look like this. That's the co-unit. C, x, y proves e, y, c. That's the unit of the existential adjunction, and so on. Okay, so that's the quantifiers as adjoint C.
Is there an off hidden in here? Because it looks like you applied the functor to the right-hand side of both and to the left-hand side of both, as opposed to crossing.
Did I do something wrong? Let's see. So let's look at the universal is on the right, and this thing is on the left. So here's this going into here, and then on the right, there's this one.
So you've got...
So the star operation goes from here to here.
That doesn't apply to star operation.
This applies to star operation. This is formulas with at most x1 through xn3.
Yes.
Above the line.
Yes.
This is formulas with x1 through xn, comma y3. This is formulas with at most these things 3. The fact that this thing doesn't actually have a y in it says that it's in the image of the star operation.
Ah, okay.
Yeah? And that's kind of that's the overlookable, kind of trivial operation to which quantification is adjoined. Now, there's another story that I could tell about this is provability in first order logic. Right? There's another story that I could tell about the proof theory of first order logic. And what that would give us, in the same way that the proof theory of propositional logic gives us the simply typed lambda calculus, what that would give us is the proof theory of first order logic. What is that? So I think I'm going to finish up by making a big table here, and then we'll call it good. The proof theory of first order logic is dependent type theory. Right? So there's another story that I could tell about the sigmas and pi's, which are the propositions as types, dependent type theory version of the provability quantifiers for all and exists. In just the same way as conjunction and implication are the provability versions of the proof theory in the lambda calculus that is product and exponential. Is that an analogy that makes sense to everybody?
Can you take that one more time?
Yeah. I think I'm going to make a table, and then maybe it'll work out. So, first of all, let's look at propositional logic. See if we can fit this in a table like this. So on the one hand, there's provability. By which I mean just the idea that P proves C without P proves Q, say, without knowing why. And then there's the actual proof theory of this notion, proof theory. which is really the same thing as type theory, simply typed lambda calculus. So what's that? Well, that's saying something like, take an assumption U of P, and from that, get a proof term T of Q. So that's the Curry-Howard, if you like. This is provability, just there exists some proof. This is the actual calculus of proofs. Good? Everybody's familiar with this, I think. So from a logical point of view, what do we have here? We have here propositional logic. So something like maybe intuitionistic propositional calculus. So it's got conjunction, it's got implication, maybe it's even got disjunction. Okay? From a proof theory point of view, we have the proof theory of this. So we've got type theory. This is simple type theory, if you like, or also called lambda calculus with simple types, simply typed lambda calculus. So it's the lambda calculus with products and function types, and maybe also with sum types. Good? That's something everybody knows. Yep. And now what I've done is I've given you a kind of category theoretic analysis of these things in the following terms. So here's the category theoretic or the algebraic way of looking at this thing. What is this? This is a poset, partially ordered set, which is Cartesian closed, poset, Cartesian closed category. Right? Cartesian closed poset. It's really the same thing described in a different way. Or if we add these coproducts here, we have the notion of a Heiting algebra. Heiting algebra. If we go over here and we look at the whole thing, not just the provability, but the actual proof theory of it, we got the notion of a Cartesian closed category. Right? That was a category with products and exponentials, possibly with sums if we want to put the sums in there. So what we have down, so whereas this is looking at provability and this is looking at the whole proof theory, what's really going on down here from a category theoretic point of view is something different. Well, not much different, but a little bit different. And that is, this is a general notion of a category. And this is the special case of a category, which is a preordered category or a poset category. Yeah? We take the category in general or the category with just at most one arrow between two things. There's another interesting adjunction that I haven't had time to talk about, but maybe you can think about it. These are sum among all the categories. There's an adjunction going like this, with the left and right like that. And that's an interesting thing from a logical point of view too, right? It takes every category to its poset reflection. And it's a really neat way of analyzing the Curry-Howard setup that you're familiar with here from a type theoretic point of view in terms of category theory. Okay, so this is a whole table for propositional logic. Let's do the same thing for first order logic and see what happens. I don't know if I can fit it in here, but I'll try. Maybe it's not wise to do it in the same place. Well, what the heck. First order logic. For first order logic here, what does provability in first order logic correspond to? Well, this is the intuitionistic first order logic, right? So it has quantifiers A and E, and then it has of course, also the propositional logic. So this was the logical point of view, and then this is the categorical point of view down here. What's over here? The proof theory. So U, P, say T of type Q. The proof theory, this is now dependent type theory. It's lambda calculus with dependent types. I don't know if people are familiar with this, or maybe it was my job to do this, or did somebody else already do it? He said a lot about this. If I had had more time, I would have been happy to do it. It's a great, very expressive and comprehensive theory. It consists of expressions like this, right? Where this type now can depend on this variable. That's the type dependency going on there. So not only can this term depend on this variable, but this type can also depend on this variable. And then you can make sums and products of such dependent types. And you get a very expressive calculus. So that's dependent type theory. And in terms of these operations, one can recover the usual simply typed operations. And usually you put in some basic types, maybe 0 and 1, the type of Booleans, maybe the type of natural numbers. So that's a very rich and expressive theory of typed first-order logic. Okay, so what's the category theoretic thing corresponding to this? Well, there is, of course, a notion down here as well. I haven't had any time to talk about this. This would be the notion of a heighting category. And really, you know what it is if you know the rest of the terms in these tables. You can work out what this has got to be. Right? It's the thing that corresponds to this in the way that this corresponds to that. Now, there's an interesting space left here, right? What is the proof theory of first-order logic from a categorical point of view? Here it was a Cartesian closed category. Here it's what's called a locally Cartesian closed category. And a locally Cartesian closed category is a very robust structure in the same way that Cartesian closed category is. The definition of a locally Cartesian closed category is a category E with the property that for every object X, the slice category, which we talked about before, is a Cartesian closed category. And it turns out that that captures exactly this notion of dependent type theory, in the same way that this captures exactly this notion of the simply typed lambda calculus. And there's a completeness theorem, and there's a kind of back and forth construction. And in both cases here, I'm not saying that these two lines are somehow similarly motivated or they look the same or something. I'm saying there's a very tight connection between these two lines, right? Given something like this, you can construct one of these out of it. Given one of these, you can construct one of these out of it. And the operations, if you compose them back and forth, will be isomorphic to the identity. So I haven't defined that yet, but that's what's called an equivalence of categories. These are equivalent categories. You make a category of these and a category of these, and these categories are equivalent. It's the same thing looked at from two different points of view. And that holds over here, too. These two lines, these represent equivalent categories. Here in this case, which is just the poset case, and here in this case, too, which is the general categorical case, there's an equivalence of categories between locally Cartesian closed categories and dependent type theories. So these are just two ways of looking at that same structure again. And maybe finally, just as a kind of application, I'll mention the fact that this completeness theorem that I told you about before for Cartesian closed categories, namely, or rather for the simply typed lambda calculus, the completeness theorem for the simply typed lambda calculus was based on the fact that the Yoneda embedding, if C is a Cartesian closed category, then we know that the Yoneda embedding from C into presheaves on C is a Cartesian closed functor. That is, it preserves all the Cartesian closed structure. Well, something stronger is true. Namely, if C is a locally Cartesian closed category, then the Yoneda embedding from C into sets, into presheaves on C, is also locally Cartesian closed. That means this beautiful Yoneda functor preserves not only products and exponentials, it preserves sigmas and pi's. It preserves the locally Cartesian closed structure. It preserves the interpretation of dependent type theory. This thing is a locally Cartesian closed category, and this preserves the locally Cartesian closed structure. And as a corollary, we have the same kind of Kripke completeness theorem, Kripke completeness, with respect to just things with a poset in the exponent, completeness, for dependent type theory, right? For Martin-Löf type theory, if you like, for the full system of Martin-Löf type theory with sigmas and pi's. So, and the statement of it is just the same as before, mutatis mutandis. Okay, thanks for your attention.